let's continue with a three-dimensional case because we live in a three-dimensional world. So in these cases, it's often convenient to express psi as a function of r, theta, and phi, where r, theta, and phi are defined as follows: the spherical polar coordinates. Okay. So in terms of x, y, and z, okay, if this is your point right here, for example, okay. So if you imagine that this is the corner of the room, that's the back wall, okay, and this is the front of this is where the door is, okay. So I'm standing right here. So the coordinate of my head, let's say, is p. How do I get my z value? You just connect my head to the wall with a string and make sure that that's perpendicular to the wall, right? So z right there, that's my z value, the z-axis, z coordinate of my point. And so to define theta, okay, you imagine sweeping an angle from the z-axis to the line that's connecting my head to the origin, and that's theta. So that's a right triangle right there, that's a right angle. So r times cosine theta is just going to be equal to z, okay? And to get to the x-axis, what do? You drop a perpendicular line from the point to the floor. So this is the floor. The xy plane is your floor. Okay, so this y-axis is the x-axis. This is your floor, right? So this will be where my feet would be, right? So if I'm standing over here, that's where my feet would be. So connect my feet to the origin, which is that corner of the wall right there. And the angle you have to sweep from the x-axis, that is your phi. Okay? So that's phi right there. And what is that phi equal to? Well, this length right here, okay, if this is theta, okay, then this length right here is the same as this length up here, right? So if this is r cosine theta, that's your z, then this projection, this is called the projection on the x-axis, on the xy plane. This projection is r times sine theta. Okay, so if this is r sine theta right here, okay, if I drop a perpendicular line from the projection to the x-axis, so this is another right triangle right there, okay, then you can see that this length right here, this one right here, that's my x, right? My x is the hypotenuse, which is r sine theta, okay, times cosine of phi, because there's your phi right there. So this, the x coordinate, the x value right here is the adjacent side to phi. So it's r sine theta times cosine phi. And similarly, you can show that the y coordinate, which is this length right here, is going to be r sine theta, the hypotenuse of the projection, which is the projection, times the sine of this phi. Okay, so what are the possible range of values for theta and phi and r? Theta can go from 0 to pi over 2. Okay, so the range for values for theta, 0 to pi. Okay, 0 to pi. The range of possible values for theta is 0 to pi. Theta equals 0 means what? Pointing to the North Pole, pointing to upward, right? Theta equals pi over 2 means pointing to the negative z direction. Okay? So that's the negative z-axis. What is theta for a point on the xy plane? Look at it from the side. So if you look at it this way, here's your z-axis, this is your xy plane, right? You're looking at it from the side. What is theta for any point on the xy plane? What angle does the z-axis make with the xy plane? 90 degrees. So theta is pi over 2. Okay? Any point on the negative z-axis, theta equals is equal to pi. Okay? Any point on the z-axis itself, theta for that point is going to be 0. Okay, so the range of values for theta is from 0 to pi. What's the range of values for phi? Phi can just go anywhere from 0 to 2 pi and around the xy plane. Okay, so the range of values for phi is 0 to 2 pi. And the range of values for r would be 0 to infinity. At the origin, r is 0, and infinitely far away from the origin, r is infinity. Okay? Now, the differential element of volume in this particular case, dx, dy, dz, the equivalence of dx, dy, dz in this case would be r squared dr sine theta d theta d phi. How do you get that? Let's go from one spherical shell to the next. The difference between those two would be what? Dr, right? So let's say go from here to here. That's dr difference. So let's take a sample there of your three-dimensional space. Okay. Now this is going to be a difference between the top one and the bottom one. So this difference right here is dr, right? The difference between going from this to this would be d theta. But that's a difference in the angle. What's the length of that? R d theta, right? You got it? That's the length of the arc. The actual length, the difference in the angle is d theta, but the difference in the length of that arc is r d theta. Okay, so you have an r d theta and an r dr. Where does the rest of this come from? Let's see, we got two dimensions. What's the third dimension that we're dealing with? It's this one right here, right? This is a difference of d phi. What's that length? It's not r d phi because you're looking at this circle up here. The radius of that circle is r sine theta. Okay? This length is along this circle over here, not this circle. Okay, so it's r sine theta d phi. So that differential element of volume you have is dr times r d theta times r sine theta d phi. So that gives you r squared dr sine theta d. So you have r squared, okay, dr sine theta, and then d theta d phi. Okay? So when you're integrating over all possible space, then you say, if you want to integrate over the entire volume, d tau, right? Then you have to integrate whatever psi squared you have. So I integrate psi squared d tau. Whatever psi squared you have, what you can do is you multiply it by r squared and integrate over r from r equals 0 to infinity. You get the result, which will still have the r dependence is going to go away, right? Because when you integrate with respect to r, the r disappears. So it might still be a function of theta and phi. So the result of that, what do you do? So the result of that, you integrate this time. This time you multiply it by sine theta, and then integrate over theta. What's the range of values for theta? 0 to pi. And then the result of that will no longer have the r and the theta. It will just have a phi dependence. You integrate over phi from 0 to Okay? So that's what you need to do in 3 dimensions. All right. So let's apply that to a couple of questions here. Write down the integral equal to the probability of finding a particle in a sphere of radius a. So what do we need to do? We need to integrate psi squared. Okay. What do? We multiply it by r squared and then integrate over r from r equals 0 to a. That's the radius of the sphere. And then what do? We integrate over theta. So whatever the result, we multiply by sine theta. Integrate over theta from what angle? 0 to pi. Okay, remember your theta only goes from 0 to pi. And then after that, you get now an expression that just depends on phi. So you integrate over phi from 0 to 2 pi. Okay? Now, if you are going to say the particle is in that sphere, then that integral is going to be equal to 1. If the particle is not necessarily in that sphere, it could be anywhere, then that integral is going to be less than 1. Okay? Oops, sorry. You got it? So what would be the integral of that's equal to the probability of finding the particle in a spherical dome above the xy plane of radius a? So if I have a xy plane right here, okay, so here's my x and there's my y, okay, and so this is radius a. So I have a circle, right? The bottom of the dome is a circle, correct? But that dome has a radius of a, so the top of that dome is the z-axis for that is a, right? The z value. What's the probability of finding the particle there? What will we have to do? Integrate psi squared, multiply it first by r squared, and then integrate over r from r equals 0 to a. And then the result is multiplied by sine theta, and then we integrate from theta equals what? 0 to pi over 2. Why 0 to pi over 2? We only want to take the top half, right? So above the xy plane. Okay, and then finally we integrate with respect to phi from 0 to 2 pi. Okay? So that's the probability of finding it in a spherical dome above the xy plane. And if the dome happens to have a radius of a. How about this one? What's the probability of finding the particle in a spherical shell of inner radius a and outer radius b? In other words, I have two spheres. One sphere has a radius of a, and the second sphere, the spheres are concentric, they have the same center, and the radius is radius b. Let's make that homework. Okay. And some exercises from Atkins.